Welcome back to My Rubber Heart. Today we are diving into a concept that is at the very heart of rubber compound behavior, tangent delta. If you've ever looked at a dynamic mechanical analysis report or optimized the rubber for vibration damping, rolling resistance, or wet grip, you've probably come across this term. But what does it actually mean? Why do we measure it? And what can it tell us about the performance of a rubber part, whether it's in a tire, an engine mount, or a shoe sole? Let's start with the scientific explanation. When we talk about tangent delta in the context of rubber compounds, we are dealing with the property of viscoelastic materials, that is, materials that have both elastic and viscous behavior. Rubber isn't just a perfect spring that stores energy, nor is it a perfect damper that absorbs energy. It's a bit of both. When you apply a cyclic force to a rubber compound, say stretching and releasing it rapidly, it doesn't snap back instantly or completely absorb the movement. Instead, part of the energy is stored elastically and part is dissipated as heat due to internal friction. This is where the storage modulus, or G prime, and the loss modulus, G double prime, come in. The storage modulus tells us how much energy the rubber stores and recovers, essentially the elastic or spring-like part. The loss modulus tells us how much energy is lost as heat, the viscous or damping part. The tangent delta is the ratio of these two values, G double prime over G prime. So, the higher the tangent delta, the more damping or energy loss there is relative to energy storage. A lower tangent delta means the rubber is more elastic and efficient at returning energy. Now, let's take a step back and explain this like we would to a child or to someone who doesn't speak the language of rheology. Imagine you have two kinds of rubber balls. One is bouncy, like a super ball. It springs back when it hits the ground. The other is soft and squishy like a gummy bear. It doesn't bounce much, and if you just throw it down, it just splats and sticks. The bouncy ball is like a rubber with a low tangent delta. It stores and returns energy well. The gummy bear is like a rubber with a high tangent delta. It absorbs and loses energy instead of bouncing back. And to make it even easier to picture, tangent delta is like the personality of the rubber when it's jiggling. It is a dancer that bounces with rhythm and springs back in time, or is it a couch potato that just flops and soaks up all the movement? That's what tangent delta tells you. So how do we measure this tangent delta in real life? We use a tool called a dynamic mechanical analyzer, or DMA, or sometimes a rheometer. It applies a small controlled oscillating force to a rubber sample, usually in tension, compression, or shear, and measures how much the material resists deformation and how much of that resistance is stored versus lost. By doing this across a range of temperatures and frequencies, we get a complete picture of how the compound behaves under real-world conditions. So why does this matter so much? Because different applications need different tangent delta behavior. For example, in tires, we look at tangent delta at specific temperatures. At 0 degrees, we want a high tangent delta in the thread to give us good wet grip. That means the rubber will dissipate energy on the road surface and keep the tire from sliding. But at 60 degrees, we want a low tangent delta in the same rubber to reduce rolling resistance and improve fuel efficiency. We don't want energy to be wasted as heat. In vibration isolators or engine mounts, a high tangent delta is desirable because you want the rubber to absorb vibrations and keep them from passing through to the chassis. That's energy loss by design. But if you are making a springy seal or a resilient gasket, you want a low tangent delta so it maintains its shape and rebounds quickly under cyclic loads. The same goes for footwear, conveyor belts, sporting goods, and even electrical insulation. Tangent delta helps you decide whether the rubber will spring, sink, or stay still when life hits it over and over again. So, to wrap it up, tangent delta is the compass that tells you how the rubber will behave under stress, whether it bounces, damps, or does a bit of both. It's a simple ratio, but it opens up a world of insights when you're engineering rubber to perform in the real world. Thanks for tuning in to My Rubber Heart. If you've worked with tangent delta in your compound design, or have any favorite tricks for tuning damping behavior, drop it in the comments. Like, subscribe, and hit the bell icon so you never miss an episode. Until next time, stay elastic and stay curious.